run out a few seconds, so if you watch it, you can see it later. And now let's see if I can do this without destroying everything. So let's just go ahead and wipe everything clear. With that reaction, or with that question, you were asked to rank methanol, CH3OH. Is that right? So the first thing to do would be to convert everything into a Lewis structure so you know what you're looking at. Okay, we just showed what the other option was. And I'm going to draw it the way I would draw it, because I think that doesn't give away the answer right away. Okay.
Are you doing number 2 where you rank the acids?
Yes.
I don't think that was on there.
It's right there.
Oh, the 2, which I thought talking about the 6.
Oh, no. So trying to decide the acidity between these two compounds. Okay. The first thing that you should do would be make sure you're comparing the correct thing. Okay. If we're going to look at ranking acidity, it's helpful to know what our definition is. So we'd be looking at our Bronsted-Lowry acids, and our Bronsted-Lowry acid is defined as, we're looking at a proton donor, also known as H+. Okay? So we need to go through each of these compounds and identify that hydrogen. Okay, which hydrogen is the acidic hydrogen? So if we start with our first compound, methanol, we've got 4 hydrogens in there. Of those 4, only 2 are unique. And of those 2, only 1's the acidic one. So what we're comparing is going to be this hydrogen versus this hydrogen. Which of those hydrogens is the acidic one? Okay, the one on the oxygen. This is something, regardless of people coming to me and saying, I don't understand anything about acidity. If I ask this question, almost everybody boxes in the oxygen. You just ranked acidity. Okay, so you are doing it. You just start to panic when it looks more complex. Relax, you're doing it right. Okay? So why is the one on the oxygen more acidic? The oxygen is more electronegative than the carbon. It's already taking most of that electron density away from the hydrogen, making the hydrogen more positive. Okay? If we go through and now look at the other structure, again, we're in a similar situation. We have 2 different types of hydrogens. Which one is more acidic? Again, the one on the oxygen. Why? Same reasoning. Okay? It's more electronegative. Okay? So now that we've got that set up, we want to try and compare. So we can go based on the 2 first easy rules. What we're comparing in that case is the stability of the conjugate base. Okay? Do you see a base up there right now? Particularly a conjugate base? No. So what do we have to do? We got to draw it. Okay? The conjugate base is the result of losing that hydrogen. So we can go through, draw those on. We didn't do anything to those hydrogens, so we'll leave them there. Our oxygen has 3 lone pairs, and we'd end up with H+. If H+ comes off, what happens to the oxygen? It's now a minus. We'll go through and do the same thing with the other one. Oh, let's zoom in a little bit, see if I can draw that a little bit better. We get our lone pair, or an extra lone pair on that oxygen. It's still going to be negatively charged. And our carbon, still positive. And sorry, I forgot the H+. Okay. For those of you that have asked for help from me or ask in the future, most cases you'll notice that I don't draw the H+ when comparing the acid strengths. Why would I ignore the H+? It's the same in both cases, which means there's no need to look at it because it's not going to evaluate or change my evaluation of it. Okay? So we'll look for stability of where the negative charge is. Okay? First 2 rules are size and electronegativity. We look at where our negative charge is. It's on oxygen in both cases. Is there a difference in size or electronegativity as we change from oxygen to oxygen? No. Okay? So then we've got to push to our other rules. We can look at induction. For there to be an inductive effect, we're going to look an atom further away from our negatively charged species, and if necessary, continue to look atoms and atoms further away until we find an element that is different between the two structures and is more electronegative or less electronegative. So if we go out one atom, we find carbon in both cases. That's not particularly helpful. But we go out one atom more and we find hydrogens. Okay? None of those elements are particularly electronegative. None of those elements are going to contribute to our acid strength. Okay? So that's not particularly helpful, so we have to move to the next rule, which was resonance. So to go through and do resonance, what we're going to do is move electrons, in particular lone pair electrons or pi electrons. So when we're dealing with resonance, those are the only electrons we can move. They will adjust through the structure into or out of pi bonds, or onto or off of atoms, as far as lone pairs go. So we can start with our first structure. Okay? So we want to find electrons. Do we have a pi bond? No. So we need to look for another source of electrons that we can move. What other electrons can we move with resonance? Lone pairs. Do we have a lone pair? Yes. So we'll take that lone pair and we're going to try and move it. Okay? As far as our oxygen is concerned, there's only one bond, which means there's only one place I can make that pi bond. So we'll push those electrons over. Okay? Now we have to evaluate what happens to the atoms around it. Okay? What happened to that carbon? It now has an extra pair of electrons around it. So its octet is now exceeded. It's up to 10 electrons around it. We have to break a bond. We have to alleviate that stress. If we're going to do resonance, the only bonds that we can move are pi bonds. Okay? Do we have a pi bond around that carbon currently? Bit kind of an odd question. What does the arrow show? We've got an arrow showing the formation of a pi bond. So absolutely, we have a pi bond. So what do? We take that pi bond and we break it. What's the net result? Nothing. Which means what about resonance? No resonance. Okay? So when trying to evaluate for resonance structures, move the electrons anyway. See what happens. Where it's going to become tricky is if we drew this out in the nice abbreviated format, you might see something along these lines. Okay? Our abbreviated format would be that. Then when we move the electrons there, oh, that just looks like a double bond to a carbon. That can't be that bad, except what's implied. A carbon, since I've only shown one bond, I have 3 hydrogens implied. So one of the trickiest things when it comes to resonance is realizing that those hydrogens are implied, and you have to make sure you imply them before you start moving electrons into them. Okay? Otherwise, you may lose track of them and might start to draw a structure that doesn't exist. Yes?
So let's say the carbon was positively charged. Would it just be like a line and then a positive?
So,
you think that it only had 2 hydrogens?
Oh, yes. So if that carbon was positively charged, back over here, so if we had that structure, we abbreviated ethanol, and I wanted to show that carbon was positively charged, now positively charged. Because of that and all of our rules before, we know that if carbon is positively charged, it has how many bonds? 3 total bonds. One's shown, which means the other 2 must be hydrogens. Okay? So yes, you might see something like that. Typically, you won't see a positive charge floating out on a group like that because it looks ugly. It's not easy to see what atoms are attached, and it typically causes a little bit of panic. Okay? So in most cases, you won't see that floating positive charge. Okay? If we go to our other compound, and we take a look at it, we want to now see if we can stabilize that negative charge. So if we're going to do resonance, we'll start at our electron source, our negative, and we'll move it the only direction we've got for a pi bond. Okay? What happens now? What happens to that carbon? How many bonds does that carbon now have? 4 bonds. Is it okay with 4? Yeah. Oxygen's okay with 2. Everything's happy, so we can go through and draw the result of that structure. And because it's resonance, we can go through and show that double-headed arrow to represent that we're drawing resonance. Okay. What charge is on that last structure? It's neutral. Okay. So now if I'm going to try and determine which of my starting acids were the most acidic, so now we've got to go all the way back to the beginning. What we were attempting to do was to look at the stability of the conjugate base. Okay. If my conjugate base was stable, the acid was more acidic. Okay. It's always a comparison in this case. So which of those 2 compounds would you predict to be more stable? This one or this one? The one without a charge. What does that mean? The goofy one that I didn't give you a structure for was more acidic. Why is that one more acidic? Resonance. So we can come up with the statement that the conjugate base was more stable. That is absolutely true, but that doesn't really give me an explanation. You pretty much said that it's more acidic because it's more acidic. Okay, that's kind of what saying the conjugate base is more stable is. Okay, so take it a step further and say resonance stabilizes the conjugate base. That one makes that one more acidic. That kind of makes sense? Okay. So it's these kind of stepwise thoughts and conclusions that you need to be making as you process these individual problems. And yes, as the semester goes, you have to continue to do this kind of stepwise thought. Okay? Questions about that? Okay. Let's see if it works. So we've already talked about intramolecular forces. This is the last time I'll show this slide. In fact, I thought I'd already gotten rid of it. Okay. Remember, using these will help you understand where you have partial charges. Those partial charges can tell you something about the reactivity of our molecule, particularly as far as acids and bases go. Why did it not go? Oh no, it's freezing. Okay, now it'll probably jump on me. Acid and base strength, we came up with those 4 rules. The 2 most important ones are the first 2, size and electronegativity. Okay? The other ones are important as well. We just won't see them quite as often. Okay, so make sure you're aware of them. Gonna work this time? What's that? Yeah. Okay, this is going to get tedious. Functional groups, I changed this slide ever so slightly to include all the names now. So this is how I would name each of these functional groups based on their characteristics. So that should help out. We went through and talked about it, and I wrote out all their names, so it's the same stuff as before. You're going to be responsible for all of these functional groups by the end of the semester. Okay? So just kind of be aware of that. You will continue to learn, and you'll have to continue to identify them as we go. Why is it? Get it to work. We ended with classifying a pair of molecules, I believe is where we stopped. Trying to understand the different relationships between each of these. If I remember correctly, we didn't look at the last one, the last example, or did we do that one? Anybody remember? Did we do these? Yes? Okay, let's try a different one then. Yeah, because we don't have stereoisomers on there. Let's try versus should have brought the model kit. Dang it. What's that? Big component, yeah. What's the relationship between these 2 molecules? We need to go through and evaluate each of our classifications. Do they have the same molecular formula? Yes. Are they superimposable? So this one's a little bit trickier. Okay. What does the wedge represent? It's coming at you. The dash represents going away. So if we tried to pick this structure up and slide it over on top, the carbon backbone aligns perfectly. But then what about the chlorines? They don't. So we could say, okay, well, I need the chlorine to overlap, so let's take this structure and flip it. Okay. If we flip it, what happens to our carbon backbone? And we see something along those lines. Now the carbon backbone doesn't overlap. Okay. So what we end up finding out is that these two structures are not superimposable. Okay, which means we now shift into the isomer definition. So now we can look at the same atom connectivity. So when we went to structural isomers, I mentioned something about naming, which we're going to look at in just a second here. Okay. The other thing that we can do is look to see where the chlorine is physically bound. So if I went through and tried to number this out, how many carbons? And this still isn't working right over here. Is this working? Yes. Oh my gosh. Technology sucks. Nomenclature. So we got a bunch of rules as far as nomenclature goes. These are abbreviated rules for the alkanes, which are ultimately going to be the simplest nomenclature. Not rule number 1 or rule number 0 is my personal favorite. I hate nomenclature with a passion, which means if you have a nomenclature question, it's probably not a good idea to ask me. Okay? I will try my absolute best to answer questions. When it comes to the exam, I will ask very straightforward questions. So things that you should be able to name. There aren't weird exceptions or things like that as far as putting it together. Okay? And I'm very lenient when it comes to nomenclature grading. Okay? As long as the bulk pieces are there, I'm pretty happy with it. Okay? After that, rule number 1, find the longest continuous chain. Okay? The most common mistake here is everybody likes to think in linear straight lines, so you only identify the ones that are in a straight line. Unfortunately, molecules can bend, and particularly test questions, molecules can bend, and the longest chain may not be in a straight line. Okay? So make sure you find the correct longest continuous chain. Once you've got that, you can name the chain based off of the base name. Okay? So this is where you would go through the number of carbons. So if there's 1 carbon, it's meth. Then 2 carbons, F, prop, bute, pent, hex, hept, oct, non, dec, undec, dodec. Anybody know any higher than that? Good. Tridec, tetradec, quintet, dec, hextet, dec. I actually don't know beyond that. I won't ever test you that far. Your homework may very well test you that far. One of the nice things about homework, though, you have the textbook. Look it up. Okay? I don't expect you to have the homework memorized. I expect you to be able to go through and work problems from the homework to be able to learn it. Okay? After you go ahead and get the base name down, then you can identify any particular functional groups within it. Okay? At this point, we're only looking at alkanes, and we'll probably throw in some halogens just to mess with you a little bit. We'll talk about those in a second. And we can change the suffix based on the functional group. If it's just carbons and hydrogens and no double or triple bonds, the ending is -ane. Okay? If it's an alkene, you move to an -ene ending. An alkyne, you end to an -ine ending. If it's an alcohol, you get an -ol ending. If it's an amine, it's even better. Okay, we just call it a straight up amine. Okay? So some of the suffix ends for those functional groups kind of make sense, some of them don't. I did list off all of the common ones a couple lectures ago. Okay? Once we've got that identified, we can go through and number the carbons, okay, that you've now identified in your longest continuous chain. You want to go through and number it such that when you look at where your substituents are, you assign the lowest priority or the lowest number to your highest priority substituent. Okay? Again, it's alkanes right now, so that's not super relevant. When we look at a few examples, it'll come back. Okay? We can then go through and name each substituent or each branch off of the main chain according to whatever functionality it has associated with it. If it's just standard carbons, we'll change the suffix to a YL to represent a substituent. Okay? Last thing, assign your numbers to each substituent. Put everything together in one big name. And I believe it's correct to put the substituents in front of your base name according to alphabetic rules. So A, B, C, D, all the way through. Okay? One thing I do want to caution you on when it comes to nomenclature is what we're going to be discussing is the IUPAC nomenclature. Okay? There is such a thing known as the common name system, which is a little bit more of a pain to deal with. Ultimately, it just came from the initial discovery of simple molecules. Those initial discoverers came up with a name that they thought was reasonable, but ended up kind of being lost in history as far as its sense. Okay? So some of the common names will show up in both the IUPAC system and just kind of around. So be aware of that. So if you see a name that you don't know or don't recognize, please feel free to look it up. Google works well. Your textbook works well. You can always send me an email as well. Okay? So what do I mean by that? Acetic acid is one of them, yes. Here are the more common ones that you'll end up seeing when it comes to the common names. So first off, if you have only one carbon, that Okay? If you have only one carbon, our name is meth. Because it's a substituent on our main chain, we change our suffix to the YL and we end up with methyl. When we move to the next one, 2 carbons. Okay? There's no different way that we can arrange 2 carbons and still attach it to a structure. So we end up, again, with only a simple name. Okay? And we get ethyl, eth for there being 2 carbons. When we move up to 3 carbons, if it's attached in a nice straight chain, that works great. We'll name that as we would expect everything else. We'll go with propyl. Okay? You might see an N-propyl in there. N is supposed to stand for normal or something along those lines. It's not required, but you might see it there. If we have a propyl chain, though, we have more than one possible place. We could bond it at the end where this is shown, or we could try and bond it in the middle. That changes the overall structure. And what you end up seeing is what's being shown over here, kind of this Y shape. Okay? Or if you kind of squint your eyes and think about it really, really hard, it almost looks like the ISO shape. That's a joke. I have no idea where ISO came from. Okay? But the common name that you'll see for that particular shape is ISO. If there's 3 carbons in that shape, we'll call it isopropyl. Okay? Just to make things complicated, because I know it's fun to do that, we could go through and name this based on IUPAC rules. The IUPAC rule takes this group and says, okay, position 1 is now defined at the spot where it attaches to the main chain. So that's this hanging bond. So we now have carbon number 1, carbon number 2. So the isopropyl group could also get referred to as the ethyl group. But it's not just an ethyl, right? It's an ethyl with a methyl. So what we end up calling this one is we've got an ethyl saying it's a substituent on the main chain, but we now have a methyl substituent on our substituent. So how do we specify that? Methyl ethyl. Where was the methyl located? On which part of the ethyl group? On carbon number 1. So we could call this 1-methyl ethyl.
If it was on 2, it would just be a propyl.
It would be a propyl. That typically gets put in parentheses because that is now the equivalent to the isopropyl group. Okay? And if we didn't put it in parentheses, this 1 might get confused for being a substituent on our larger chain. Okay? Understand why I don't like nomenclature? These are just the simple examples. Okay? One of the nice things about nomenclature is they apply the rules evenly and fairly across the board. If you try and look at any other chemistry, biology, physics, and try and look at their nomenclature systems, they make this look amazing. Okay? Because most other systems, no one sat down and said, okay, this is how we're going to name it. Anybody tries to name it anything else, we're going to punch them in the face, which is effectively what they did. Okay? Said these are the rules, you must follow these rules. Okay? So you have to have all the rules memorized to be able to apply them correctly. Okay? So that was just 3 carbons. What happens when we get to 4 carbons? Well, we still have our possibility for butyl if it's just a straight chain. But now we can get a variety of ways to rearrange that. Okay? If we take a look at the next option here, what shape do we see right there? See the iso shape. But now it's not 3 carbons. Now our substituent is hanging off out here. There's an extra carbon there. So we can't call it isopropyl because there's an extra carbon. So what do we call it? Isobutyl. Because now there's 4 carbons in my iso group. Okay? If we move further on down the line, what if we take our standard straight chain, except this time instead of bonding it to the first carbon, we put a bond to that second carbon. Okay, that's what they're trying to show here. So second carbon could make sense for a sec butyl, for second carbon. It's not quite where it's coming from, because if that was the case and we move here, they call it tert, and that's definitely not a third carbon. So what is this second tert that they're referring to? It's not sec for second, it's sec for secondary. Secondary has a very particular meaning. You might also see it referred to as second degree. What is that referring to? Right idea. If we take a look at that carbon where it attaches to our main chain, that's our critical piece. That's the linchpin of where the sec comes from. Okay? That carbon, even in our next structure, has the same number of bonds. So it's not just, I think I got that spelled right, tertiary. It's not just the number of bonds it has. It's a very particular type of bond that it has. How many carbons are attached to this carbon? Not including the main chain. 2. Secondary. How many carbons are attached, in our last case, to our primary carbon that's not attached to the main chain? 1, 2, 3. Tertiary. Okay? That's where the sec term comes from. That's where the tert term comes from. Okay? We're trying to refer to how it's being attached to the main chain and how that affects the overall name. Okay? You could take this a step further and look at 5 carbons. I'll leave you to look at the textbook for that. Okay? Some of the nomenclature system kind of makes sense. Like we just went through, we explained where the sec and the tert come from, and that sort of vaguely makes sense. Okay? If we try to go through an IUPAC name these, say our sec butyl, just for the heck of it, let's get some practice on this. How many carbons are in our substituent? We get 3 carbons. We won't count this because that's not part of a consecutive chain. So we can circle our largest consecutive chain, and we've got 3 carbons, which would be propyl. But it's not just a propyl chain, it's a methyl attached to the propyl. So we have a methyl propyl. Where's that methyl attached? Carbon number 1. So we have 1 methyl propyl is the equivalent of sec butyl. Okay.
You would have the number before that of the carbon in the chain that it attaches to.
Yes.
Okay.
What about the isobutyl group? There's our main chain. So we still have propyl. We still have that methyl. Where's the methyl located? Carbon 2 in our chain. So isobutyl could get referred to as 2-methyl-propyl. Okay? Kind of vaguely, sort of. A little yes and no all the way through. Okay? Let's push this a little bit further to some real examples so we can stop looking at these substituents, which makes it a little more difficult to analyze. That didn't move forward. Yes?
Why was that one considered the number 1 spot?
See if this is actually working now. So what we're looking at is that carbon, which you'll notice isn't attached to anything. We haven't specified an atom out there. That's where it attaches to the main chain. Okay, so it's just their notation. So if we were going to attach this to, say, a hexane, we could then go through and say 1, 2, 3, 4, 5, 6. Sorry, ran out of space.
So you don't necessarily read left to right?
No. Left, right, up, down, backwards, forwards, all changes, depending on what structures you're evaluating.
When you say substituent, you mean?
How it's
Opposed to
attached.
another.
So if we looked at, I'm going to have to add some carbons to this. Let's add one more to make sure we're clear here. So if we were going to name that last compound now, we'd want to go through and identify our longest carbon chain. So what I would recommend you do is go through and kind of circle your longest carbon chain. So we could start, if we were going left to right, and say, hey, here's carbon number 1. So we go 1, 2, I only see 3 carbons going down, I see 4 carbons going up. So 1, 2, 3, I can count 4, 5, 6, 7 carbons, right? Everybody count it? Everybody agree? Okay, so that's one way we could have circled it. But what if I'd started down here? 1, 2, 3, 4, 5, 6, 7, 8. Which is longer? 8, which means I have to name based on my orange group. So we'll call that an oct what? So, shoot, shouldn't have circled it yet. Okay, so let's go through and show, there's our main chain. Our main chain has 8 carbons in it, so we're looking at oct for our name. I don't want to get that far yet. Our next step was the suffix. What functional group are we looking at here? They're just alkanes, just carbons and hydrogens, no fancy double bonds, other things, so we'll call it an octane. Okay. Is it just octane, or do we have something attached to the octane? We have something attached. What is that something that's attached? We could call it tert-butyl. Okay, we'll put the YL there because it's a substituent. It's a part of the main chain. Okay. What was I doing? Butyl? Butyl. You might also see T-butyl. In fact, that's all right probably is T-butyl instead of the tert-butyl. Where was that T-butyl group? What position? So now we have to go back to our structure and number our carbons to decide where our tert-butyl group was attached. So let's go through and say, okay, there's carbon 1, go away, 2, 3, 4, 5, 6, 7, 8. So we would say it's at position 5, except what happens, don't do that, if I counted the other direction. 1, 2, 3, 4, 5, 6, 7, 8. Which way is the proper way to number? The lowest number possible, which means 4 T-butyl octane. I know. Okay? Kind of makes sense? So it really just comes down to the rule. If you know the rule, you just apply the rule and count it all out, and it adds up. Okay? If you don't know the rule, you're SOL. There's no other way to get around it. Okay? One of the other things that I usually like to introduce when it comes to nomenclature, nope, it's not going to work for me. We'll talk about that in a second. First time I took organic chemistry, I failed. I had to take it a second time around. Second time around, I again went through this big stress thing trying to get through the class, and it just bothered me, and eventually I just said, okay, I need to look at it from a new start. So I went back through and decided what I thought was the most important part of organic chemistry, and to me, it was the reactivity. What can you do with each of these molecules? How can I build and move onwards? Okay? Nomenclature tells me nothing about how to build. It tells me how I can talk intelligently with somebody else. How many of your tests are verbal tests? None of them. So I looked at it and said, nomenclature is useless. Makes up about 10% of my grade. Screw it. So when it showed up on an exam, I ignored it. Completely skipped over it, continued on, which is one of the reasons why my nomenclature is so bad, because I never spent the time to learn it. Okay? That said, at the end of the semester, I got an 89%. Which was a B, okay? Which sucked. If I'd spent any effort learning nomenclature, I could have had an A, okay? So spend your time wisely about where the material falls. I really kind of despise the fact that I lost an A because of something that's so stupid. So when I write tests, the nomenclature does not make a large percentage of the test. Okay? By not, I'm looking at 5%, okay? 5 to 6% of your test. So it's something that you want to decide is not relevant and you can skip and move on past. By all means, go ahead and do that. be aware your homework assumes that you're learning nomenclature, and the questions asked in the homework will involve nomenclature. So you will have to use some of it. Okay? The things that I test on are the bulk things. How many, or what's the name for 1 carbon? What's the name for 2 carbons? Up to 6 carbons. So you can use some kind of knowledge to apply that information. Getting down the exact numerical order, did you count the correct direction? I don't particularly care. If I can take your name and draw the structure, I'm happy with it. We'll move on from there. Okay? One more thing about nomenclature, because it'll pop up partway through, so we might as well finish off with our nomenclature. Cyclic structures change, because if we take a cyclic structure, say a 6-carbon cyclic structure, what's the longest carbon sequence? Well, if I start here, I count 1, 2, 3, 4, 5, 6. Well, there's 7, 8, 9, 10. We're in a cyclic structure. That doesn't work very well. Okay, so how do we circle? Okay, so what we'll end up doing is changing our nomenclature a little bit to represent that it is cyclic. So one of the big things that we'll add into it would be adding the term cyclo. Okay, and then when we go through and count, we don't continue to count all the way around, which is usually a good idea why you should circle. And now when we go back through, we end up with 6 unique carbons. Yes, we have a space there, but that space we can finish off by calling it cyclo. So in this case, I've got a 6-carbon ring. 6 carbons is what name? Hex. I don't have any double bonds, triple bonds, or other functional groups, so it would be hexane. It's a cyclic structure, so it becomes cyclohexane. Okay? There are some things that change on this. Your first substituent is by definition at position 1. Okay, so if I go through, draw out this cyclohexane again, and I put on that. Okay, here, let's make it more creative. Let's do another one. Okay, we can still go through, circle our main chain. Our main chain has 6 carbons, so we're looking at hex. No fancy functional groups, so we get hexane. It's a cyclic structure, so we get cyclohexane. Now we have to name any substituents. So we'll look what we haven't circled yet. And if you're one of those people that has lots of colors, it's usually a good place to use those colors. Circle anything that's outside of our main chain. How many carbons is that? 2, which means we're looking at an ethyl. The last part is trying to number where that ethyl is on our ring. Well, our ring is very symmetric. It's kind of difficult to tell. That's why we decide that your first substituent is always at position 1. So when we name this completely, we get ethyl cyclohexane. We don't have to add the 1 in front because it's convention. It is going to be at position 1. If you want to include the 1, you're not wrong. I'll probably just cross it out and move on. Okay? If you have multiple substituents, this you can see again where I run into weaknesses. I believe they're numbered alphabetically to give the lowest total numbers. Okay, when you move into cyclic structures, the exact numerical order on how you number things takes on some weird rules. Okay? Your textbook does explain them. Any organic instructor other than myself can probably explain them really well too. Okay? Just realize on the exam, I want to see what the pieces are and a good attempt at numbering them. You don't have to nail it down perfectly. Okay? Questions about that? Take a look at some examples. Of course, this isn't working. So, let's try some examples. Okay. So let's go ahead and start with the upper left-hand corner. This one's going to be a little bit tricky because we've got those goofy parentheses in there, which are going to mess with it. Okay, so probably a good first step would be to draw this out and a line angle format, so it's a little bit easier to see. So we're going to have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. That then connects to this carbon. 1, 2, 3, 4, 5. Carbon 6. Carbon 6 connects to 2 more carbons. So 1, 2. Carbon 6 is also connected to 3 other carbons. 1, 2, 3. Sorry, I ran out of space there. Can you guys see that? I will take silence as a yes. I guess that's fair. Okay? So we now need to go through and circle our longest chain. Okay? Since we've got it written out, it stands out a little bit more obvious. We're probably going to start circling over here, easiest way to go through. And we get to carbon 6. Which way do we go? Up or down? Up, because there's 3 carbons there versus 2 carbons down. If we went back to our straight drawing or a formula, if we tried to circle, we would circle and drop off sequence. You see that? So depending on the structure, you may not be circling something in a straight line. Okay? We could go through and name our main chain first. We've got 1, 2, 3, 4, 5, 6, 7, 9 carbons. I know I said you didn't have to memorize that, so you don't have to worry about it. That ends up being non. Do we have any fancy functional groups? Functional groups. No, so our ending is ane. Do we have any substituents? Okay. Before I include the name into, or include the substituents into the main name, I typically write it outwards or outside my main name so that I've got that labeled down. I now need to go through and number and decide where to number from, left to right, right to left. Should be right to left, I think. 1, 2, 3, 4. Our ethyl is at position 4. I then go through and say 4 ethyl nonane. Okay? Yes, no.
One more time, just what did you just do?
For getting the ethyl. So the green, what we went through and did is we named our main chain that we had highlighted in orange, which gave us 9 carbons, which gives us the non-name. The ane comes from the functional group. We're just carbons and hydrogens, no double or triple bonds, so we've got non-ane. We then need to evaluate, do we have anything else outside of our orange line? Yes, we do. That's now circled in green here. What's the name of that? 2 carbons gives me an ethyl. I then need to specify where that ethyl group is on the main chain. I've got 2 directions I can number, from right to left or from left to right. If I go right to left, my ethyl is at position 4. If I go left to right, it's at position 6. 4 less than 6, it's 4 ethyl. I should continue doing this until I have all of my substituents named, okay, which is why I've got this written out separate. Okay? Because that's my last substituent, or my only substituent, I can then combine it with the rest of my name. And I get 4 ethyl nonane. Make sense?
But how do you know when, say, you just had the full methyl nonane and you didn't, I mean, you would put the substituent off the board, and it would be like a totally different structure than what we have there.
Good question. What's my name? Uh-oh. Am I putting you on the spot too badly? What's my name? Jose. Okay, I can accept that. What's my name now? How about now? Does my name change depending on how I'm moving? No, it's irrelevant. Same thing's happening to the molecule. Okay. What we're doing is naming it based on the current conformation that we see. If we draw it where we picked this up, flipped it, spun all those bonds around, it's still the same compound. And it would still come up with the exact same name, which is why when we number to find the shortest position, it doesn't matter if I pick the structure up and flip it. It may look like it's closer to the left, but it's still at position 4. Okay? And that's one of the trickiest things with nomenclature, is you have to take into consideration that if the molecule moves, do you get the same name? And if you don't, there's something wrong. Yeah. Okay. Did I count wrong?
Healing.
I asked that originally, but I know what the counting on now.
Okay.
He added on to the 3.
So,
Yeah.
whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9.
You're counting the first written row, right?
I'm going the first row.
Right.
So if you look here, is that what you're looking at?
Yeah,
There's only 8.
That's the
This was the big issue. So when you look at just a straight line, you have to realize that your longest continuous chain may not be written in a straight line. Why did I circle the orange, not the black? Because the orange is longer. My main chain includes a zig there, or a zag, I guess, depending on your perspective. Looks more like a zig. Okay, so you end up with 9 carbons. So if you count this out, did I count it wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a 4 right there, saying that we get 4 carbons in sequence. I did count it right, didn't I?
Yeah, maybe the confusion is
It was just the way when you did the branch off, because I was looking at the 8 and 9 too.
Okay.
I think people just.
It's just the 2 that
One
that you don't have circled were part of your first written line,
Yes.
and then you add the 3 from the second line, and
Yep.
that's where you're probably getting confused. As far as the 9 really.
Yep. And what we're trying to do is convert, ultimately, a formula, which we said was useless to begin with, into a structure. And when you go through and name, you're not naming formulas, you're naming the structure. Sometimes it's easy to see they're in a relationship, sometimes it's not. So when you go through to name, make sure you draw out a structure, because the formula may not match up nicely for you. Okay, other questions on that? You think you got that line down? I picked that example for that very reason. You have to make sure you count the longest continuous chain, regardless of where that chain goes. Okay, let's try the next one. Where are we going to go with that next one? Upper right. So you're saying 6, I'm hearing pent, and I'm hearing a lot of people count probably up to 7 or 8. Why 6? There's our longest chain. The cyclic structure trumps in this case. If our substituents had more than 6 carbons, then we could name our ring as a substituent off of that main chain. Because
You can't count around the circle.
you won't count the groups off of it, because those can't count as continuous as far as the ring goes.
So that always drops everything.
Yep. So if we went through and tried to name this, what do we end up with? We get 6 carbons in a ring, so we've got hex. We get a cyclo, and it's an ANE. Okay, this is where my nomenclature is going to bite me. I meant to look up this answer again just to make sure I got it right. Okay, the rest of this part, or the rest of this, is now trying to name the substituents around it. So we can go through and now circle those in a different color. Okay. What substituents do we have? What's the upper right one? We get the T-butyl group. Whoops, that was an accident. You should include that little hyphen in there, but I don't blame you if you don't. What's this group? Oh, shouldn't be that close. We get a methyl. And this last one, also a methyl. Okay. We now need to specify where each of those groups are. Okay, so we have to come up with some way to number this that we can get these things correct. Where should we start our numbering? I think it's the T-butyl. I really do, but I'm not positive. So if the T-butyl, we're going to start our numbering there. So this is not where I would test you on it. That would then be position 1. Where are our methyl groups? So the way you guys went through and numbered it was 1, 2, 3, 4. Why didn't you not number that direction? You get larger numbers. Okay, good. So you got that figured out. So we've got 1 T-butyl. We have a 2-methyl. And we have a 4-methyl. How do we put our name together? So when we compile everything, and I'm pretty sure I get this one right, we want to make sure alphabetically we organize our substituents in front of this name. T-butyl starts. We ignore the T for some reason, I think. Okay? I didn't come up with the rules. Don't look at me. So we get 1 T-butyl. Okay? We now need to specify the location of our next substituent, so we'll put in another hyphen. I'm going to run out of space here. Okay? So you should always put hyphens in between letters and numbers.
You're right.
What's our next substituent?
It is alphabetical, and it doesn't include that.
It doesn't? Good. What's our next substituent?
Methyl.
2-methyl. So we could write 2-methyl. But then what's our next substituent? 4-methyl. So we'd be repeating ourselves twice, saying methyl twice. Is there an easier way to do that?
2, 4.
We can then add a comma and say we now have a methyl at position 2 and 4. You'll notice there, if you can tell, there's a large space there. Why is there a large space? I must specify that there's multiple methyls. I have to include the dimethyl. So the name here becomes 1-T-butyl 2,4-dimethyl cyclohexane. And that's a short name. Okay? So it's a question of slowly piecing it together to try and build your structural name. Okay, the last thing that I'm going to do with nomenclature, hopefully for the moment, so I want to talk about more interesting things, would be looking at what's wrong with this name. Okay, so we should go through and try and process this. We're now going to go the reverse direction, from name to structure. Where should we start with our name? Where do you think most people would like to start? Oh, the left side of the name, and just go full through it. Okay, so 3-ethyl. So we can draw an ethyl. Where is it attached? Position 3. Where's position 3? We haven't got it drawn. Okay, so instead of starting left to right, start with the main part of the name first. We'll start with our hex. Okay, and then evaluate outside of that hex to make sure you're not looking at a cyclohex. There's no cyclo in front, so we're looking at a hex structure, which means 6 carbons. 1, 2, 3, 4, 5, 6 carbons. The ane ending means we don't have any special functional groups, so we can leave it as the ane. The next part is going through and evaluating our substituents. We have a methyl, dimethyl, and those are located at positions 1 and 2. So where's position 1 and 2? We can number any direction we want. So where are you going to put number 1? Left or right? Left. Okay. So at the left position, I'm going to put on a methyl. Okay, for position 1. What about position 2? We need another methyl. Okay. We can now move through to the next part of the name. We get to ethyl. Where's the ethyl located? Position 3. And I can put the ethyl on. You notice that I may be drawing these kind of oddly. That first green one I drew up. The next one I drew up, and the blue one I drew down. Why would I draw like that? Looks pretty. That's about it. Okay. If you build a model kit, you'll notice that the structure naturally does take on this kind of shape when you kind of extend it out in a straight line. So what we're trying to do is represent that 3-dimensional shape as best as possible. Okay? So, yes.
With the, one methyl on there, why
Yes.
doesn't it become a 7? Why does it say 6? Oh, because I didn't read
What's wrong with this name? It's not a hexane. It has to be a heptane. Our longest chain is through here. We'd be looking at a heptane, not a hexane. Your textbook asks these questions, and if you take a look at exam number 1 from last semester, I asked this dumb question too. And everybody was like, what's wrong with his name? I can't draw it correctly. So yeah, watch out for that. You might see things like that. If it shows up, just raise your hand, say you might want to check your work. I'll probably tell you to move on while I go through and verify that I screwed up or did it correctly, and then let the whole class know. Okay? So look over the what's wrong with these name problems, because that can help you evaluate and find where the rules go. Okay? Questions about that? Can't believe I spent an entire lecture on nomenclature. Yeah. So, structure to name, circle the longest chain, name the longest chain. Circle each substituent, name each substituent, number in such a fashion that your substituents pick up the lowest number, put everything together, you pretty much have your name. Okay? When you're going name to structure, I would ultimately interpret going right to left instead of left to right. Okay? I didn't perfectly do that, but I came pretty close to interpreting it from right to left. Okay? So that should help you evaluate those a little bit better when trying to work with them. Okay? Consequences of single bonds. So we already kind of talked about this. We can get free rotation around that sigma bond. Okay? Because as I rotate, the overlap never changes. Okay? Those hybrid orbitals always stay overlapped. Okay? So that's kind of an interesting repercussion of double bonds. And it starts to affect other interpretations or other views on the structure. So we briefly talked about drawing another view. All of these represent the same compound. We're looking at ethane, which would be CH3, CH3, right? And if we looked at it from just kind of really, really simple perspective, we could look at it in the line angle format, which is very similar to what they had drawn. Could add on our hydrogens. You might see someone go through and draw wedges and dashes like I've got them drawn here. Again, why would I choose to draw the wedges and dashes as I've got set up, where they're on opposite sides? One wedge and dash is aimed down, one's aimed up. Okay. Some of it has to do with space. Another part of it has to do with how the structure actually exhibits itself in 3 dimensions. I could have just as easily have drawn this. All of these drawings represent the same structure. Why do I pick one over the other? And they're all pretty equally messy, so we can't pick something like that. Okay? And the reason comes back to what this is starting to show, and which on Wednesday I'll have the model kit to actually show you a little bit more of. If instead of looking at the structure from the side, where our hydrogens are coming out at us, we're going to now rotate that front carbon and bring it out towards you. So we bring that and rotate it out. Okay? We're now looking at the structure from a different perspective, which means when we draw it, we have to draw it from a different perspective. Okay? The first guy to go through or guy that got credit for it at least, his name was Newman, and he generated the Newman projections, which will be pretty much everybody's least favorite thing. Okay? And we end up with yet another 2-dimensional view of a 3-dimensional structure. And you'll notice that we start to see some very odd shapes or drawings come out of it. So let me draw the side view of each of these compounds first so you can get an idea of what's happening with it. So there's our carbon, carbon, hydrogen straight up, Hydrogen's coming at you. Hydrogen's going away. If you have a model kit, this is huge as far as figuring it out. Okay? So that's that first one. We've taken that front carbon, which I'll now color in blue, and I've now rotated it towards you. So if we now look at the structure, Newman's projection here, where is that front carbon? Okay, it's going to be right in the center, and this is where it gets a little bit weird. If something's coming at you, typically what happens? It looks bigger. But if we have something behind it, say that back carbon in red, would you be able to see that back carbon? No, so we lose information. So what Newman came through and did is thought, let's do some reverse perspective. We're going to make the front atom small so that I can then see the back atom behind it. So our front atom is blue, and that's our little point right in front. And it's now bound out to those hydrogens. Our back atom, or our front atom, is connected to the back atom through a bond. That bond we can no longer see because it's hidden behind our atom. Okay? Our back carbon is now that giant big circle. And it's got its bonds out to its hydrogens. Okay? This orientation, the wedge is aimed down and at you, wedge is aimed down and at you. If we rotate that structure out, let's see if I can do this. So it's like this. Okay? My hands, or my or the hydrogens, or we can even make it, no, we'll go straight out. Aim straight at you. If we turn the structure, what happens to those bonds? They overlap. Okay? Or if we get really fancy with our terminology, they eclipse each other. And so what we're looking at is an eclipsed conformation. So all we're trying to do is see what a rotation about that bond does as far as our structure goes. Okay? If we try and do the same thing with the other one. Okay, so let's go with our blue and red again. So there's our blue. Except now what we're going to do is instead of convert from our line angle to our Newman, we'll try and go from the Newman to the line angle, which is a lot trickier. Okay? Same general idea. We're going to go through and rotate. We're going to rotate that blue carbon, our front carbon, down to the left. Is that left? That looks like left. Okay? Which means when we look at our structure, our blue carbon should be where? On the left-hand side. So there's our blue carbon through a bond that we can't see to our back carbon. Let's look at the bonds on our blue carbon. Where's this?
Did you shake it?
It's all right here on my screen, too. What the heck? Fine. Just draw it. Take that, technology. So, we said the blue carbon was the one in front. We're rotating that down to the left. So as we do that, we've got our blue carbon with the bond that we can't see, connected to our back carbon. Okay, so there's our back carbon. So let's try and show where our hydrogens are. This hydrogen should be where on this structure? So we take it, it's straight up and down. So here I am, straight up and down, and I turn. Straight up and down still. Okay, if we take a look at these hydrogens, okay, and we turn. One's coming out, and the other one is going away. Where are those? So again, if I got that general shape, where would they be? Above or below? Above. So we've got a wedged hydrogen coming up and a dashed hydrogen going up. Let's take a look at our back one. We got that hydrogen again, straight up and down, and we turn it. Still straight up and down. Nothing to, that's me, right? Yeah? Okay. No one acknowledged. I got to keep going until I get some acknowledgement. If we look at our other hydrogens, we got one coming out, one going back, but aimed downwards. Okay? And what we've drawn now is our line angle conversion from the Newman to our line angle. So why would we pick one over the other? Well, if you take a look at our Newman projections, we can pick some extra information out of them. Would we expect one of these to be more or less stable than the other? And the question becomes is why? Okay. What does that line represent? What's in a bond? Electrons. What do we want electrons to do? Or what do electrons want to do? Spread out and get the most space possible. So they want to be as far away from any other electrons as possible. If we take a look at this one, how many other bonds are near? Roughly, what is that, 60 degrees away from two other bonds. Take a look at our eclipse one. It's actually overlapping another bond. Okay, it's in the same plane. Where would that bond prefer to be? Down below. Okay, where it has more space. Okay, so what does that mean about energy if we're looking at a preference? This one, lower in energy. So when I drew out the structures, you'll notice that I naturally go into drawing this. Why do I draw this? Because that represents this Newman projection, which happens to be a lower energy Newman projection. Okay? So the idea is to always try and draw and represent these things in as low as energy as possible, because that's the most likely state that we'll find them in. When we then try and do reactions with them, again, it's coming from we're picking that most likely populated state and trying to see where we can move from there. Okay? So between these two conformations, we get two different names for them. You get eclipse, which kind of makes sense, and staggered, which also kind of makes sense. Those bonds are staggered away from each other, 60 degrees. Okay? Turns out if we make our compound a little bit more complex, is it putting? Yeah, it is putting stuff up. Instead of just carbons and hydrogens, let's add an atom X. Atom X is not a hydrogen, so it's now something larger than a hydrogen. Okay? We'll find that we can get, come on, two more possible orientations in the staggered conformation. If you go back and evaluate your eclipse conformations, you'll also find that you can get different eclipse conformations. Okay? Should we care about the different eclipse conformations? Why not? They're all really high in energy anyway. Why bother to look at something that's high in energy when we're compound's not going to likely be there? Okay? So I don't subcategorize the eclipse conformation. You should be able to look at them and decide which one's higher or lower in energy, but I won't ask you that directly. When we move to the staggered conformation, you'll notice that we can get two different types of orientations. Atom X, where we're still staggered, but atom X's are close to each other. There's another option where now atom X is far away from the other atom. Which of those would we expect to be higher or lower in energy? Pick your pick. The bottom one should be lower because, why does it need to be further away? X is larger than hydrogen. What makes it larger? What does it need? Electrons. If X is larger, it has more electrons, which means it wants more space. Which means I want to get them as far away from each other as possible. Okay? So the most common conformation is going to be to line those X's up away from each other. We'll start with this on Wednesday, but I'll attempt to put on the funny names for these. You get gauche for left because this x is on the left of that x. Yeah, that didn't make any sense. That was supposed to get that kind of response. This one makes a little bit more sense with the anti. X is opposite each other across our single bond. Okay, so we're in an anti-transformation. Gauche stands for left, I think, in French. You guys speak French? Gauche. Okay, it means X's are closer to each other. That's what it means in French. Right? So, take a break if you're in lab. We are still going to meet here for lab. Don't go run off to lab. We'll talk a little bit in the end of lab. This is officially a 2-week lab, so we're going to do it 1 week though.